Hello everyone, how are you doing? Today we're going to discuss integration in this video. I'm going to show you what integration really means. So stay tuned, stay with me. So let's start. So we have a basic idea of calculating the area of any human-made shape, that's a triangle or a quadrilateral or any other shape. So let's have a rectangle here, right over here. Let its height be h and its width be w. Then we calculate its area to be equal to height times its width. This is the basic idea of calculating the area of any human made shape. But guys, nature doesn't work according to us. But for example, we have a curve right over here. So if we need to calculate the area under this curve, so this stuff, if we need to calculate the area of this stuff, it's not even close to any human made shape. So you can't just compare it to a rectangle and or any human made shape and just apply the height into width, so and get the area. So it was a big problem in the ancient mathematics, but a guy named Riemann came up with the idea of dividing this area into small rectangles. He said that if you need the area right over here of this stuff, you need to divide this stuff into small rectangles and then sum up the area of those rectangles. And the more you divide this stuff into the rectangles, the more close you get to the area of this stuff. So the more close you get to the exact answer. You can't get to the exact answer by this approach. You can approximately be closer to it. So just said let's divide this area into small rectangles. We have divided this stuff into small rectangles. So he said, let this be y equals to f of x, this curve be equal to y is equal to f of x. So the Riemann said that with the more number of rectangles there will be, the more accurate the area will be. So what Riemann did was, he said the area of this stuff will be equal to the summation, let k be a dummy variable n, and the n is the number of rectangles you are dividing the area into. So the summation from 1 to n, the height, the simple idea, height f of x, because f of x, when you put any value of the x into f of x, it will give you the rise of the curve, or y, that's the height. It will be f of k xk, that's f of xk. So because you will put x1 x2 x3 and so on, that's its k, it will work according to the dummy variable. So guys, it will be f of xk times the width of every rectangle, that's w. This was the basic idea what Riemann thought of, but Riemann was not quite satisfied with this idea because he was a mathematician and he needed an exact answer. But this stuff right here will give you the approximate area under that curve. So what he did was simple. He started putting limits, the language of limits, into this. What he said was, if we have a rectangle, let its width be equal to dx, that x, its width is infinitesimally small. So what we can do is, we can do two things. We can just make the number of rectangles tending to infinity, and or we can just make the width of the rectangle tending to 0 so that we can get an exact area under the curve. So he said that area under the curve will be equal to limit, the first thing, n tends to infinity, where n is the number of rectangles you're dividing the area into. It will be equal to the limit n tending to infinity summation of k from 1 to n f of x times the width. This was one thing, and the other thing we generally use is limit dx, the width, the infinitesimally small width of the rectangle tending to 0, and the summation of k from 1 to n f of x. Now right here the width is dx. But now the problem was almost solved, but the remaining problem was right here. This thing, the sigma or the summation, sums up the integer values, but here we are going to infinitesimally small value of dx, which tending to its dx is infinitesimally small, or we can say the series above right here, sorry guys, the series right here will be infinitely long. So what he did was he tried to do something like this. He tried to make this stuff to be contained in a single symbol. He started with S. He thought of S, but S was used. S is still used to represent displacement. So he thought of doing representing this stuff with stretched S. That's area A will be equal to the stretched S f of x times dx. Now the whole thing, the limit and the summation, is contained in this stuff S right here. This S and this thing, let's write it again, be more clear. So f of x dx, this thing solved the whole problem, and this is what we call as Riemann's integral. So, and the process by which we solve this stuff is called integration, what we are discussing about. Now if you guys get confused about why we're calculating the area under curve, it's a simple curve, why you are calculating the area under it. So let's clear that out, why we're doing this stuff. For example, let's have this. We have this right here. We have a line with a y-intercept of 3. Let's raise this a little bit. Y-intercept of 3, and its rise be equal to up to 13, and at x it will be equal to 5, say 5. So simply if we calculate the gradient, the simple formula for the gradient is rise over run, but if we introduce it to the language of limits, then we can write it as dy upon dx, that is, we are going infinitesimally small. So if we calculate m, the gradient will be equal to rise, that's 13 minus 3, over run, that's 5, that's 10 upon 5. The rise is equal to 10 and run equals to 5, that's gradient equals 2. But we can rewrite this stuff, we can write it again like rise is equal to m times the gradient times run. Let's just write it as dy coming up from this be equal to m gradient times dx. So sorry guys, we come here, it comes right up from here. Rise is equal to dy over here, and run equals dx over times the gradient. So let's just, if m our gradient equals to 2, you know m equals to 2, then our gradient function will be something like this. This will be equal to 2. This is m in this direction, and this is run in this direction, run over here. And if we need to calculate this, we have run equals to 5, and if we need to calculate the rise, so we need to calculate the area under this m and the run, the gradient and the run. The area of this will be simply equal to 10. Hope you get it. But let's remind from where this 10 came from the last scenario. This 10 was here equal to 13 minus 3, that was the rise. If we go back to this problem, this stuff over here, this will be equal to 13 minus 3 from the first scenario equals to 2, the gradient 2, and dx equals to 5 minus 0. Now we can develop a shortcut by the Raimond's thoughts, by the Raimond's thinking, by what Raimond gave us. We can develop a shortcut by just calculating the primitive of an integral. We can just calculate the primitive. That means if we want to calculate the area, we can just subtract this. If we subtracted 13 minus 3, we would have just got to, this will be 10, and this will also equal to 10. This is a simple thing. So guys, thank you for making me a part of your day. See you soon in the next video. Thank you. Bye bye. Khuda Hafiz.